Welcome back to the deep dive. This is where we take, a whole stack of compelling sources and really boil them down into the crucial insights you need to be well, truly well informed.
Absolutely.
And today, we're embarking on a journey into a concept that honestly pushes the very boundaries of our imagination.
It really does.
We're probing the edges of what's currently possible and maybe what might one day reshape our entire interstellar future.
A big topic, for sure.
Think about it, right? Our innate human drive to connect, to reach out across distances through time, has always propelled us forward.
Yeah.
We started with, primal drumbeats echoing through valleys, then smoke signals carrying warnings.
Right. Simple stuff, but effective for its time.
Exactly. Then light-flashing Morse code across oceans, the astonishing reach of radio waves spanning whole continents.
A huge leap, radio.
Huge.
Yeah.
And now we use incredibly precise lasers to communicate with deep space probes light years away. Each leap just redefined what we thought was possible, always pushing the envelope. How fast can our messages travel?
And that drive is still there. We're always looking for the next step.
But even with all this incredible progress, our most advanced communication methods, and they mostly rely on electromagnetic waves, right? Whether that's visible light, radio, microwaves.
Yeah, the EM spectrum.
They face some pretty fundamental, unyielding barriers. These waves, they can be absorbed by dense matter, scattered by cosmic dust, distorted by gravitational fields.
Or even deliberately jammed, intercepted, too.
Right. Imagine trying to send a text message to someone on the other side of a black hole or trying to have a clear radio conversation through a massive solar flare.
It just wouldn't work. The signal gets lost or scrambled.
It simply won't work. These technologies, as amazing as they are, operate within the limits of their physical properties. But what if there was another way? A way that transcends merely communicating through space to maybe communicating with the very fabric of space itself.
Okay, now we're getting to some really interesting territory.
That, my friend, is precisely the mind-bending concept we're diving into today. Gravitational wave communication.
Ripples in space-time carrying messages.
Exactly. Could the very ripples in space-time themselves carry our messages across the vast silent cosmos, totally undisturbed by anything in their path?
It sounds like pure sci-fi.
It does. But for this deep dive, we're drawing from an incredibly insightful and rigorously researched source, the Gravitational Wave Communications exploratory paper. This was penned by Dr. Lev Nemotin, who's the CEO of N5 Digital Inc.
Right, and listeners might remember Dr. Nemotin from our previous deep dive. We looked at the raw physics of gravitational waves then, based on his work too.
That's the one. His profound understanding of this field, really steeped in theoretical and practical exploration, informs the groundbreaking ideas we're about to get into. It grounds what might sound like fantasy firmly in well-known physics.
He's careful to distinguish between theoretical possibility and current engineering reality, which is crucial here.
Absolutely. So, to really understand this, our mission today is to peel back the layers of this extraordinary concept. What would it actually mean to communicate with gravitational waves? What makes them so uniquely special? And what are the colossal, almost unimaginable engineering and scientific challenges we'd face trying to harness them?
That's a great way to frame it. And what's particularly fascinating here is how Dr. Nemotin approaches this topic. This isn't just, speculative storytelling. It's a rigorous inquiry, a scientific what if, but grounded in the fundamental physics that might one day enable such an astronomical leap.
Okay.
So we're going to explore not just the theoretical possibility, the what if, but also the practical how, or maybe the how difficult, for a communication channel that seems, in principle, utterly unstoppable. A true cosmic bypass that could redefine interstellar connection.
A cosmic bypass. I like that. Okay, let's start setting the stage then. Let's trace humanity's relentless quest for better communication.
Right, the historical context.
For millennia, our advancements have really revolved around finding more efficient and far-reaching wave carriers. From the limited range of sound waves in the air,
shouting distance, basically,
pretty much, to light waves carrying visual signals like signifiers or lamps, then radio waves spanning continents. Each discovery just dramatically extended our reach and improved the fidelity, the clarity of our messages.
Think about life before radio. Sending a message across the Atlantic took weeks, months maybe, by ship.
Unbelievable now.
With radio, it became instantaneous, and then lasers let us talk to probes way out past Mars, even heading out of the solar system. It's been this continuous, accelerating march forward.
An unbroken march. And this continuous evolution is absolutely critical context. You're right. All these technological marvels from our humble Wi-Fi signals in our homes.
Right, streaming this deep dive right now, perhaps.
Exactly. To sophisticated satellite communication, they fundamentally rely on electromagnetic or EM waves. They're incredibly versatile. They've utterly shaped our modern world, no question.
Absolutely shaped it. But despite their power and how common they are, EM waves have inherent inescapable limitations. And these become really obvious when we start thinking about truly vast distances or hostile environments.
Like deep space.
Exactly. Imagine trying to communicate through a really dense interstellar dust cloud, or trying to get a clear signal through the swirling plasma of a star's corona, or even just a thick planetary atmosphere like Jupiter's.
It's not going to happen easily.
Right. EM waves scatter off particles, they get absorbed by dense matter, think planetary cores or thick gas, and they can be distorted by magnetic fields.
And then there's the security angle.
And that's maybe the most critical point for, say, secure interstellar communication that can be deliberately jammed or intercepted.
Yeah.
Think of the static interfering with your car radio, that's a simple example, or a thick cloud deck completely blocking satellite images, or even the huge radio silence zones astronomers need because of Earth's own EM noise.
Right. We interfere with ourselves.
We do. These are all real-world examples of those fundamental limits. Limits imposed by the very nature of how electromagnetism interacts with matter.
So it sounds like we've kind of hit a fundamental ceiling with EM waves, at least for certain applications. Their physical properties dictate these intrinsic limits. What then? What could be fundamentally different enough to break through those ceilings? Is there even a theoretical next step for communication that completely bypasses these problems?
And that's precisely the fascinating leap Dr. Moten explores in the paper. While EM waves are incredibly powerful, they interact with matter, and that creates those limitations.
Okay.
But what if we could use a wave that, well, that doesn't really interact with matter in the same way? This is where gravitational waves, GWs, step in. As the paper describes them, they're a radically different class of carrier.
Radically different, not just another...
He did. General relativity, 1916. But it took nearly a century until 2015 for the groundbreaking LIGO detectors to finally observationally confirm them.
With that famous signal, GW150914.
That's the one. The signal from two colliding black holes, that was a massive game changer for astrophysics, obviously. Opened a brand new window onto the violent cosmos.
Yeah, a whole new sense for the universe.
But for communication, the implications, as Dr. Moten's paper suggests, are maybe even more profound. What's truly fascinating here, and this connects back to the bigger picture, is that these gravitational waves interact incredibly weakly with matter, almost unimaginably weakly.
So just ignore it.
Pretty much. Unlike EM waves, they pass almost entirely unhindered through stars, through planets, even through entire galaxies. They're practically immune to scattering, to absorption, or to blockage by any intervening cosmic structures, no matter how dense they are.
Wow.
This profound, almost ghost-like difference means that in principle, they could be the perfect long-range, absolutely unjammable communication medium.
A true cosmic bypass.
A true cosmic bypass, cutting straight through all the interstellar noise and clutter. Your message simply gets through, without really touching anything along the way.
That's an incredible thought.
Oh.
But, okay, if it truly passes through everything, does that present any unique challenges for, say, targeting a receiver? Or ensuring only the intended recipient gets the message? How does unstoppable factor into precision and privacy?
That's a very insightful question, actually. And yeah, it's where the engineering challenges would just multiply, right? While the signal itself isn't hindered by stuff in the way, targeting is still about knowing precisely where your receiver is located, maybe light years away, and aiming your source with incredible accuracy.
Okay, aiming is still key.
Absolutely. And for privacy and security, you wouldn't rely on physically blocking the signal because, like you said, that's impossible. Instead, you'd have to rely on incredibly sophisticated modulation schemes and maybe quantum-level encryption, something far more robust than anything we have today.
Because anyone could potentially pick it up.
In theory, yes. Anyone with a sufficiently advanced detector could pick up the signal. The unstoppable nature means no one can physically block it, but decryption, that's a whole different ballgame.
Okay, that makes sense. So this is where it gets really interesting, because Dr. Moten frames this not just as a technical challenge, but as like a historical echo.
Right, drawing parallels.
He reminds us that concepts once considered pure science fiction, things like radio itself or controlled nuclear reactions, lasers, even space travel.
Things people laughed at.
Exactly. They later became transformative realities. Think about Jules Verne imagining submarines or H.G. Wells dreaming of trips to the moon in their time. Seemed utterly impossible, right?
But the underlying physics wasn't actually violated. It was just the engineering that was light years beyond their grasp.
That perspective really gives a hopeful, forward-looking tone to this whole exploration. It's about not dismissing something just because it feels impossible now.
Yeah, don't bet against human ingenuity, maybe. Precisely. And if we apply that historical lens, gravitational communication, while currently incredibly distant, requiring breakthroughs we can barely even conceive of, it could, in the very long term, enable humanity to communicate across interstellar distances without loss, interference, or interception.
Imagine that.
Imagine the implications. Sending a message to a colony on an exoplanet thousands of light years away, knowing it will arrive undiluted, unblocked, and utterly private from anything physical trying to stop it.
Wow.
And beyond communication, the very pursuit of this technology, the fundamental research required, that could open entirely new avenues for fundamental physics experiments. It could let us probe space-time and quantum mechanics in ways we can only dream of today, maybe reveal entirely new phenomena.
So the journey itself could be revolutionary.
Could be.
Okay, before we delve even deeper into the communication aspect itself, it's probably essential we quickly revisit the basics of what gravitational waves are, because they're so fundamentally different from anything we intuitively experience, right?
Absolutely. Good idea.
So, to simplify, gravitational waves are literally ripples in space-time curvature. Imagine throwing a pebble into a perfectly still pond. You see the ripples spreading out.
Yeah, classic analogy.
Now, try to imagine that the pond is the entire fabric of the universe itself, space-time. And instead of a pebble, you have incredibly massive objects like two black holes spiraling into each other at insane speeds.
That's a really good starting point for the analogy. These space-time ripples are produced when massive objects accelerate, but in a very specific way. Their mass distribution has to change asymmetrically.
Asymmetrically.
This asymmetric change creates what's called a quadrupole disturbance in spacetime. This disturbance then radiates outward from its source, carrying energy and angular momentum away, much like an EM wave carries energy from an oscillating charge.
And they travel at light speed.
Crucially, yes, they travel at the speed of light. And once generated, they just keep propagating indefinitely across the universe, largely unattenuated, unless they get absorbed or dispersed by cosmological expansion, which is really only relevant on the very largest cosmic scales.
Okay, so this quadrupole disturbance, that's a pretty specific requirement, isn't it? It's not just any moving mass that generates these waves. What exactly do we mean by that, and why is it so important?
That's a critical distinction. The source requirement for emitting detectable gravitational waves into the far field is very particular. Only systems with a time-varying quadrupole mass distribution will produce them.
So not monopole, not dipole.
Exactly. Let's use Dr. Nemoten's swinging dumbbells analogy, but expand it a bit. Imagine you're holding a single dumbbell. If you just expand and contract it uniformly, like inflating a balloon, that's a monopole movement. No gravitational waves.
Okay.
If you just move it from side to side without rotating it, like just shifting its center of mass, that's a dipole motion. Still no gravitational waves radiated away. Neither of those actions changes the shape of its mass distribution in the right way to ripple space-time effectively.
Needs that specific kind of change.
Right. But if you take that dumbbell and spin it end over end, or if you had two dumbbells and spun them around each other, or even if a single dumbbell were to wobble erratically, its axis of rotation constantly changing. That asymmetric motion, that changing shape of the mass distribution over time, that sends vibrations, ripples, into space.
Ah, I see.
That's a quadrupole moment changing over time, and that's precisely why binary systems, like two black holes or two neutron stars orbiting each other, are such powerful natural sources of gravitational waves. Their asymmetrical orbiting dance creates exactly this kind of time-varying quadrupole moment.
Whereas a perfectly spherical, non-rotating star wouldn't emit them.
Correct. No matter how massive it is, if it's perfectly symmetric and not changing shape asymmetrically, it won't radiate gravitational waves.
So if that's the what and how of their creation, what does this all mean for their journey?
Okay.
We're talking about something almost impossibly faint, yet incredibly persistent.
Exactly. Once generated, these waves are like cosmic highways, traveling at light speed, essentially without absorption across the entire universe. They just keep going, almost untouchable.
But their strength, or rather their weakness, that's the paradox, right? GWs are extremely weak. The Earth-detectable signals we've observed from these huge cosmic catastrophes like colliding black holes have strain amplitudes of around 10 to the power of -21.
Yeah, that number is almost impossible to grasp intuitively. It truly represents the insane sensitivity required to detect them.
Can you put that into perspective? Like, what does 10 euro mean?
Okay, let's try. Imagine trying to measure a change in length that's equivalent to a single atom's diameter, but across the entire solar system.
Oh, okay.
That's the kind of minuscule wobble we're talking about. Or, to use LIGO scale, it means that the gravitational wave passing through one of its detectors, which have these 4-kilometer-long arms, it only changes the distance between the mirrors by less than the width of a proton.
Less than a proton's width over 4 kilometers.
Less than a proton's width. That's a trillionth of a meter, 10 eurometers. It's like trying to measure a change in the Earth's entire circumference by the width of a single human hair.
That's unbelievable sensitivity.
It really is. And this extreme weakness is both the monumental challenge and the profound promise. It makes them incredibly hard to generate in any kind of human-controlled way and incredibly hard to detect with our current technology.
The double-edged sword.
Exactly. But that very weakness also means they interact so little with anything else that they propagate without loss, potentially across billions of light years, carrying information from the furthest reaches of the cosmos directly to us, undimmed and undisturbed. And this is all consistent with general relativity, confirming their reality and their unique, almost ghost-like properties.
Given that incredible persistence, despite their faintness, the core question then becomes, can we actually harness these whispers of space-time for communication? Or does nature fundamentally forbid it somehow? Are we trying to build like a perpetual motion machine here, something that just defies the laws of physics?
Dr. Niemotten's paper provides a pretty definitive answer here, and it's a crucial one. No, it is absolutely possible in principle.
Okay, that's big.
It is. General relativity, our best theory of gravity, explicitly allows gravitational waves to be produced, modulated, and detected. Conceptually, the physics doesn't impose any fundamental prohibition. It's not inherently different conceptually from how we generate, encode, and receive radio waves. The universe isn't saying no to this idea.
That's a colossal hurdle cleared right there. It immediately shifts the entire focus, doesn't it? From questioning the fundamental physics to confronting the practical engineering.
Precisely.
The barriers aren't theoretical or conceptual, they're purely technological. And these technological barriers, by all accounts, are truly monumental, almost staggering in their scale.
They absolutely are. The first, and maybe the most daunting practical barrier, is the sheer energy efficiency challenge.
The power needed.
Exactly. Producing a detectable gravitational wave signal for communication, even an incredibly faint one, would require astronomical amounts of energy. Orders of magnitude beyond anything we can currently generate or even sustain.
Like what kind of scale are we talking?
We're talking about energy outputs maybe approaching that of entire stars or the cataclysmic power released by colliding black holes. Our current technology for energy generation is simply nowhere near this scale.
Right.
This immediately puts it into a class of challenges like, say, controlled nuclear fusion or practical interstellar travel.
Wow.
These are problems that are not forbidden by physics, but they require such immense breakthroughs in energy generation, materials science, engineering, that they remain firmly in the distant future.
And then there's the quadrupole limitation we just talked about.
Right. The fact that gravitational radiation requires that time-varying quadrupole variation really constrains the types of modulation schemes we could use. It makes it far more complex than just, turning an EM signal on and off or easily changing its frequency.
You can't just wiggle an electron.
Exactly. We can't just wiggle an electron to send a gravitational wave. We'd have to somehow orchestrate the movement of enormous, incredibly dense masses with almost atomic precision.
Okay, but there's the flip side, that advantage.
However, there's that incredible no-absorption advantage. Unlike radio waves, which get soaked up or scattered easily by matter, GWs pass through matter almost without loss. That makes them an incredibly attractive, theoretically perfect channel for communication.
So super hard to make in here, but once they're going, they go.
That's the essence of it. The transparency is its superpower, but also contributes to the difficulty of interacting with it for generation or detection.
That analogy you mentioned to things like controlled nuclear fusion or interstellar travel, that really puts the scale of the challenge into perspective. It's not about if we can, fundamentally, but how and how much colossal effort and advancement that how really entails. It speaks to a future where our energy generation capabilities and our control over matter are orders of magnitude, maybe many orders of magnitude, beyond anything we possess today. It's really a vision for a truly advanced civilization.
It is a Type 2 or Type 3 civilization on the Kardashev scale, perhaps?
So, okay, if we're serious about communication, we need to encode information onto these waves. Just like we modulate EM waves, changing their amplitude, frequency, or phase, we theoretically need to do the same with gravitational waves. But how on Earth, or maybe how in the cosmos, do you sculpt space-time ripples in a controlled way to carry information? That, conceptually, is just a phenomenal challenge.
It absolutely is. The paper identifies active source control as the most feasible modulation scheme, at least in principle.
Active source control, meaning fiddling with the source itself.
Exactly. This means deliberately changing the dynamics of the gravitational wave source itself. We're imagining having precise, fine-tuned control over, say, a binary system of massive objects, perhaps two incredibly dense, maybe artificial stars or black holes orbiting each other.
Okay, so how would that work? Like for AM/FM?
Let's consider how this might work for different modulation types. For amplitude modulation, AM, you could potentially achieve this by precisely changing the separation distance between these orbiting objects. Or maybe by altering their mass asymmetry.
So farther apart is weaker, closer is stronger.
Something like that, yeah. A wider separation or a more balanced mass might produce a weaker signal, representing a 0 bit maybe, while bringing them closer or making one much heavier than the other could increase the amplitude, representing a 1 bit.
And frequency modulation.
FM. For frequency modulation FM, you'd adjust the orbital frequency of the source. The faster the objects orbit each other, the higher the frequency of the gravitational waves they emit.
Right. Frequency is tied to orbital speed.
So you'd encode information by minutely shifting that orbital speed, perhaps making the orbit slightly faster for a 1 and slightly slower for a 0. Tiny, precise changes.
And phase modulation, TM.
And for phase modulation, PM, you could vary the precise orientation or timing of the source's orbit. Shifting the phase of their orbital dance, meaning exactly when they reach a certain point in their orbit, would impose a corresponding phase shift on the gravitational waves. That allows for another layer of encoding information.
Okay, so going back to the swinging dumbbells idea.
Right. It's like imagining you could perfectly choreograph their swing, changing its rhythm for frequency, its intensity for amplitude, and its exact timing for phase, all to spell out a message.
That sounds intricate.
It's an engineering feat that borders on the impossible with current tech, requires godlike control over stellar mass objects.
This is where it gets really interesting, though, because Dr. Nemotin also considers less feasible avenues. And it's important to understand why they're less likely. One is wave interaction.
Ah, right. Can GWs talk to each other?
Yeah. If we can't make GWs talk to each other, our only option seems to be this perfect choreography of supermassive objects, which sounds incredibly complicated. Why are wave interactions unlikely?
It boils down to how weakly gravity interacts, even with itself. Gravitational waves interact only very, very weakly with each other. This means nonlinear mixing, where two waves combine to form new frequencies or directly modulate each other, is essentially negligible under most circumstances.
So they just pass through each other?
Pretty much. To use an analogy, with electromagnetic waves, you can have many different radio signals in the air at once, right? And they can interfere, mix, even jam each other. It's like an orchestra playing together, all the instrument sounds blending and interacting.
Okay.
But gravitational waves are more like lonely solo instruments playing in an immense vacuum. No jam session is possible, really. Each source plays its own lonely solo, almost completely oblivious to other gravitational waves nearby.
Which is good for signal clarity, I guess.
It makes them incredibly clean signals, which is definitely an advantage for receiving an undisturbed message, but it also means they can't be easily modulated by other waves interacting with them.
Okay, so that's out. What about third body modulation, passive stuff?
Right. The other less feasible avenue mentioned is third body modulation. This refers to passive effects like gravitational lensing or phase shifting caused by other massive bodies that the wave happens to pass by.
Like a galaxy bending the waves.
Exactly. Gravitational lensing, for example, happens when light or gravitational waves bend as they pass massive objects like galaxies or black holes. This can amplify or distort the signal, and while this is super fascinating for observing distant objects in astrophysics,
we can't control it.
Exactly. It's a natural phenomenon entirely beyond our control. It could theoretically alter GW propagation, maybe even focus it slightly by chance, but it's not something we could design or manipulate to reliably modulate a communication signal.
So not useful for sending a message.
Right. So while these avenues are theoretically interesting from a pure physics perspective, they're just impractical for designed active communication. Our focus, therefore, really has to remain on actively controlling the source itself, however difficult that may be.
Okay, that makes sense. This brings us to where gravitational waves truly shine, as you put it, as a communication medium.
Yeah.
Their propagation, how they travel.
Yes, this is their superpower.
When we talk about a communication channel, how the signal travels is everything, right? Radio waves, they're great, but they get absorbed by water or metal. Your Wi-Fi signal doesn't punch through thick concrete walls very well.
And it certainly won't get through a planet.
Definitely not.
And that's the fundamental distinction here. The paper really emphasizes the unparalleled transparency of gravitational waves. This is perhaps their most unique and compelling feature for deep space communication.
They just don't care what's in the way.
Pretty much. They pass through stars and planets with negligible absorption. That's astonishing to think about. Imagine sending a signal directly through the core of Jupiter, or even through the incredibly dense heart of our own sun, and it emerges on the other side practically unaffected.
Wow. No blockage.
No blockages, no signal degradation from intervening cosmic bodies like nebulae, accretion disks, even huge dark matter halos.
And scattering. Reflection.
Minimal scattering, except in the most extremely dense or curved spacetime, like right around a black hole's event horizon. And crucially, no reflection by ordinary matter.
So what's fascinating here is the message gets through.
The message gets through. No cosmic dust cloud, no planetary core, no swirling stellar plasma can stop it. For long-distance, interstellar, or even intergalactic communication, this is just an unparalleled advantage in terms of signal integrity and reliability. It's truly a virtually perfect channel, at least from the perspective of having an obstacle-free path.
It's incredible to think about. Dr. Nemotin does mention gravitational lensing by massive objects, how they can amplify or defocus signals.
Yeah.
But he clarifies, like you said, that while it's interesting for observation, maybe letting us see distant, faint GW sources we otherwise wouldn't.
Right, nature giving us a telescope boost.
Yeah. But it's not a controllable mechanism for design communication. It's an effect of nature, not a tool we can actually wield to shape our signal.
Exactly. So the bottom line on propagation is gravitational waves offer a virtually perfect, unattenuated channel across cosmic distances. Unlike radio, which can be jammed, intercepted, or blocked, gravitational waves are fundamentally unstoppable by any physical object in their path.
Like that analogy from the paper.
Yeah, the steel rod analogy, I think it really drives home the difference. Sound in air scatters, light in fog dims. Gravitational waves are like ripples in a steel rod stretched across the galaxy. They pass through everything without loss.
Imagine that steel rod stretching from here to Alpha Centauri.
The ripple would reach the other end with barely any dissipation.
To really break this down, this is the ultimate dream, isn't it? For interstellar communication. A truly universal message in a bottle, unhindered by absolutely anything in between.
It really is.
Imagine the implications for exploring and colonizing other star systems, or even for potentially communicating with extraterrestrial civilizations, knowing your message will traverse the void unimpeded. It truly is the ultimate cosmic express lane.
The ultimate reliable channel.
But quick question on that steel rod analogy. Does that hold up even in the most extreme cosmic conditions?
Yeah.
Like right near the event horizon of a black hole?
Yeah.
Or is that where even GWs start to get wobbly?
Ah, that's a sharp follow-up.
Yeah.
And yeah, the analogy mostly holds for the vast majority of cosmic space. But in extremely strong gravitational fields, like directly around a black hole, space-time itself becomes incredibly warped.
Okay.
In those extreme environments, gravitational waves can be significantly affected. They can be lensed dramatically, they can be absorbed by the black hole itself, or even undergo complex interactions with the black hole's own gravitational field. So while they're incredibly resilient, there are limits to their perfect transparency in the absolute most extreme astrophysical conditions.
But for communication between stars and galaxies, generally avoiding those singularities.
For that purpose, yeah, they are indeed practically perfect channels. The obstacles just aren't there in normal space.
Okay, so if we can theoretically generate and modulate these waves, even if it's incredibly difficult, and we know they'll travel unhindered across the cosmos, The next monumental challenge, and maybe the primary obstacle to making GW communication a reality, is detection.
The listening part, yeah.
We're talking about hearing the faintest whisper of space-time, often from incredibly distant or maybe incredibly faint artificial sources. The ability to use gravitational waves for communication just hinges entirely on our capacity to detect them.
That's absolutely the crux of it right now. Our current instruments are already marvels of human ingenuity, pushing the absolute limits of precision measurement.
Like LIGO and Virgo.
Exactly. We have LIGO and Virgo, these kilometer-scale laser interferometers. They're effective in the hertz to kilohertz range. They work basically by splitting a laser beam into two, sending each half down these incredibly long L-shaped arms, reflecting them off mirrors at the ends, and then recombining the beams.
Hiding the interference.
Right. When a gravitational wave passes through, it minutely stretches and squeezes space-time itself, changing the effective length of those arms by that amount smaller than a proton's width we talked about.
Tiny change.
Infinitesimal. This causes a tiny but measurable interference pattern in the recombined laser light. It's like trying to detect a tremor by measuring a shift of a few nanometers in a 4-kilometer-long ruler. The engineering needed just to isolate these tiny signals from all the other noise sources, like ground vibrations, thermal fluctuations, even the quantum noise of light itself, is just astounding.
And then there are the pulsar timing arrays for lower frequencies.
Right, pulsar timing arrays, PTAs. They're sensitive to much lower frequencies, down in the nanohertz range, which allows them to potentially detect signals from things like supermassive black hole binaries orbiting each other very slowly.
How do they work?
They use arrays of incredibly stable, rapidly spinning pulsars, which are like cosmic lighthouses, sending out regular beams as ultra-precise clocks scattered across the galaxy.
Using nature's clocks.
Exactly. If a very low-frequency gravitational wave passes between us and one of these pulsars, it slightly alters the arrival time of its regular pulses, either delaying them or advancing them by nanoseconds over years. By observing many pulsars across the sky very carefully, scientists can infer the presence of these huge, slow gravitational waves. It's like using the entire galaxy as a detector.
That's amazing. And historically, there were resonant bars, too.
And historically, yes, we had resonant bars. These were some of the earliest attempts, though they were very narrow-band instruments. Essentially massive aluminum cylinders designed to physically resonate, like ringing a bell at specific frequencies if struck by a gravitational wave of the right frequency. Less sensitive, but an important step.
It's incredible to think about the precision required for all of that. But what about the future? What's on the horizon for detection concepts that might one day allow us to pick up, say, a human-generated gravitational wave signal rather than just these cosmic cataclysms?
Well, the paper highlights several really exciting future concepts. LISA, Laser Interferometer Space Antenna, is a big one. It's a planned space-based interferometer.
Like LIGO in space.
Similar principle, yeah, but operating in the millihertz range, much lower frequencies than LIGO. By deploying 3 spacecraft in a triangular formation, separated by millions of kilometers, it would be totally free from Earth's seismic noise. It could detect a whole new range of lower frequency GW sources that terrestrial detectors just can't hear.
Opening a new window.
Definitely. Then there are more advanced terrestrial ideas like atom interferometers. These promise potentially enhanced sensitivity by using the quantum properties of atoms themselves, specifically their wave-like nature, to detect minuscule space-time distortions with potentially unprecedented precision, using atoms as the rulers, essentially.
Okay, leveraging quantum effects.
Exactly. And that leads to quantum-enhanced interferometry. This uses techniques like squeezed states of light. Now, this doesn't mean literally squeezing light. It means manipulating the inherent quantum uncertainty of light itself. You can reduce the noise, the uncertainty, in one property you care about, like the phase of the light, but quantum mechanics forces you to increase the uncertainty in another property, like its amplitude.
A trade-off.
A quantum trade-off. But for detection, this means we can potentially push the limits of sensitivity even further, getting closer to the absolute edge of what quantum mechanics allows. It effectively makes our detectors' ears inherently quieter at a fundamental quantum level.
Quieter ears, better listening.
Precisely. And then there are some more theoretical but very intriguing concepts mentioned, the Gertzenstein effect converters.
Ah, that sounds interesting. Converting GWs to EM waves.
That's the idea. It suggests a pathway for converting gravitational waves directly into electromagnetic radiation, like light or radio waves, maybe in the presence of strong magnetic fields. That offers a completely different detection pathway than purely measuring mechanical stretching. Instead of measuring distance changes, you'd be looking for a tiny flash of light or a radio signal induced by the passing GW.
A different kind of signal entirely.
Right. And superconducting RF cavities are another theoretical concept being explored for highly sensitive detection, leveraging extreme low temperatures and quantum phenomena in superconducting circuits. Lots of ideas out there.
So what does this all mean for the fundamental limits of detection then? What kind of quantum leaps, beyond just building bigger detectors, would be needed here to truly hear that faint space-time whisper, especially from an artificial source?
Well, the primary sources of noise we fight against in current and future detectors are seismic noise from Earth's constant rumbling,
And ground-based ones.
thermal noise, just the heat causing atoms in the detector components to jiggle,
Random motion.
and crucially, quantum noise, which is an inherent fundamental limitation imposed by quantum mechanics itself. You can't measure things with infinite precision.
Heisenberg limits, sort of.
Related to that, yes. The quantum nature of light and matter sets a floor on the noise. But the good news, as Dr. Moten points out in the paper, is there is no fundamental prohibition against reducing quantum noise, even if we can't eliminate it.
Ah, okay. So we can push it down.
We can push it down. Advanced techniques, like the quantum-enhanced interferometry, the squeezed light we mentioned, can effectively push these quantum limits lower for the measurements we care about. So while detection is absolutely the critical bottleneck right now, the paper suggests that with continued breakthroughs in quantum technologies and maybe these hybrid EM coupling schemes, detection could advance dramatically.
It's not a law of physics preventing it.
No, it's just immense technological barriers we haven't overcome yet. To use that analogy again, detecting a GW is like spotting ripples from a pebble dropped thousands of miles away. The ripples are incredibly faint, but if you cover the whole pond with an array of incredibly sensitive laser beams and quantum sensors, you can measure them.
That's essentially what LEGO does now.
And what future detectors will aim to do even better, pushing closer to those quantum limits.
Okay, so we've discussed the massive challenges in both generating and detecting gravitational waves for communication. It's clear that pure gravitational interaction is incredibly weak.
Vanishingly weak, yeah.
But the paper outlines several theoretical mechanisms that, while maybe wildly inefficient by today's standards, don't actually contradict fundamental physics. It kind of leaves the door open for radical advances, suggesting various avenues for how we might one day bridge this immense gap.
Exactly. These mechanisms include, first, the quadrupole mechanical sources we've already talked about, like rapidly rotating massive objects or engineered binary systems. These are the most straightforward way to generate GWs based on our current understanding of general relativity.
But the energy and control needed are insane.
Right. The sheer mass, the rotational speeds, the precision control required are currently far beyond anything we can engineer. Then there's that fascinating concept of electromagnetic gravitational coupling, often referred to as the Gertzenstein effect. This acts as a potential bridge between the two types of waves.
The translator idea.
Kind of, yeah. And as we just discussed, quantum-enhanced detectors using things like squeezed states or atom interferometers are absolutely crucial for sensing these incredibly faint signals, whether they come from a natural source or a hypothetical artificial one.
And there are even more exotic ideas.
The paper also briefly touches on even more exotic extensions for the far, far future, things like mechanisms potentially involving extra dimensions or hypothetical scalar fields from cosmology. These are highly speculative, of course, but they show how open the theoretical landscape remains if we eventually push beyond our current standard models of physics and gravity.
It makes sense to look for these bridges, these connections, especially given how weak pure gravitational interaction is. So what about these hybrid approaches? Dr. Moten discusses gravitational waves driving electromagnetic effects. Why might these be considered the most, maybe, practical route towards detection and eventually communication?
Well, precisely because of that incredibly weak coupling of gravity itself. Hybrid schemes, where the gravitational wave somehow drives a measurable electromagnetic effect, are indeed considered among the most promising directions.
Because we're better at detecting EM signals.
Exactly. If a gravitational wave can induce a measurable electromagnetic signal, however small, it could be a far easier way to detect it than trying to directly measure the infinitesimal space-time distortion itself. It's like space-time translating its message into a language. Our current detectors are already fluent in the language of electromagnetism.
So how might that work?
One key idea involves charged particles in magnetic fields. Imagine a region of space with a super strong magnetic field, maybe naturally occurring around a neutron star, or perhaps a future human-engineered one of incredible strength.
Okay.
A gravitational wave passing through this region would cause the charged particles within that magnetic field, electrons, protons, to oscillate minutely, just jiggling back and forth due to the space-time distortion.
The GW shakes them.
In effect, yeah. And this induced motion of charged particles would, according to electromagnetism, produce tiny electromagnetic signals, like radio waves or even faint flashes of light. Now, these signals would still be incredibly faint.
It may be detectable.
But they might be easier to detect with our existing highly sensitive EM technologies, like radio telescopes or optical sensors, than trying to directly measure the GW strain itself.
And the Gertzenstein effect is part of this.
The most direct form of this idea is the Gertzenstein effect, named after the physicist who first proposed it back in the 60s. This posits the direct conversion of a gravitational wave into electromagnetic radiation in the presence of strong background magnetic fields. It's not just the GW influencing charged particles, which then radiate. It's the GW itself potentially transforming into an EM wave.
A direct conversion.
A direct conversion. Now, the coupling strength for this effect is predicted to be vanishingly small. You'd need truly immense magnetic fields and incredibly powerful gravitational waves to get a realistically detectable EM signal out.
Still a huge
A
challenge.
huge challenge. But conceptually, it provides a direct bridge between gravitational wave phenomena and electromagnetic phenomena. This makes it one of the more promising theoretical directions for future research, as it offers a potential way for space-time to speak in an electromagnetic language, which we are much, much better equipped to hear.
So that analogy you used, the whisper into a megaphone.
Yeah, a gravitational wave moving charges in a magnetic field is like whispering into a megaphone. The initial voice is incredibly faint, but under the right extremely powerful conditions, the strong magnetic field being the megaphone, it becomes audible electromagnetically. The Gertzenstein effect in this context is that conceptual megaphone, potentially letting space-time speak in a detectable way.
So to really understand this, we might not hear the gravitational wave directly as that physical ripple in space-time, but perhaps we could detect its echo or its translated message in the electromagnetic spectrum, like finding a translator for space-time.
That's a great way to put it. It's a truly ingenious potential approach to an otherwise seemingly impossible detection problem, relying on finding these tiny interaction points where gravity and electromagnetism might couple.
Okay. Even if we could hypothetically produce, modulate, and detect these signals, what about their actual information capacity? Can we actually send meaningful amounts of data this way? We're talking about deep space communication here, which often needs to carry rich information, scientific data, maybe video, complex instructions, not just like simple beeps or single bits.
That's a fundamental question, absolutely. And that's where the cornerstone of information theory, the Shannon-Hartley theorem, comes in. And crucially, it applies even to something as exotic as gravitational waves.
Shannon's limit applies here too.
It does. The theorem basically states that the maximum data rate, or channel capacity, depends critically on two things. The signal-to-noise ratio, SNR, how strong your signal is compared to the background noise and the bandwidth available, the range of frequencies you can use.
More signal, less noise, wider band equals more data.
That's the gist of it. A stronger, clearer signal relative to all the cosmic and detector noise, coupled with a wider range of frequencies you can effectively modulate and detect, means you can transmit more information reliably per second.
So how does GW communication stack up right now?
Well, with current or near-future technology, as you might expect, given how incredibly weak any human-generated gravitational waves would be, the SNR for any conceivable artificial GW communication signal is far, far too low, just hopelessly buried in noise.
So zero capacity, practically.
This effectively means a zero capacity for practical communication today. We simply can't generate a loud enough signal or detect it sensitively enough against the background to make it useful for any real data transfer. The signal would be utterly drowned out by cosmic gravitational wave noise, seismic noise, thermal noise, quantum noise, you name it.
It's like trying to have a phone call in the middle of a constant rock concert using a broken microphone and a tiny distant speaker.
That's a pretty good analogy for the current SNR challenge, yes.
So it's a definitive no for now, a practical brick wall. But what about the future? Is there a fundamental ceiling on how much data we could theoretically send if we did somehow overcome these monumental engineering challenges? Or could it one day rival, say, fiber optics in terms of data rate?
And this is crucial. The paper asserts there is no fundamental ceiling on the data rate imposed by the physics itself, only practical limitations.
Oh, okay. That's vital.
It is a vital distinction. It means that the physics of general relativity doesn't inherently forbid high data rates using gravitational waves. With sufficient sensitivity in our detectors and enough power in our sources, even if that power is currently astronomical and the sensitivity requires quantum-level breakthroughs, gravitational wave communication could theoretically support any desired data rate.
So the waves themselves can carry the info if we can just manipulate and read them well enough?
Exactly. The physics doesn't impose a limit on how much information a gravitational wave could carry per second. It's purely about our technological ability to encode that information onto the wave, generate it strongly enough, and then decode it accurately from the noise floor at the receiving end.
So the message from the paper is clear here.
Yes, the message is clear. The physics doesn't say no, but the engineering challenge remains immense. It's all about how much loudness we can achieve for the signal at the source and how incredibly well we can filter out the noise at the receiver.
And that requires huge leaps.
It requires not just incremental improvements, but potentially entirely new paradigms of energy generation, quantum sensing, material science, and information processing. But if we could somehow generate GWs as easily as radio waves and detect them with similar ease, the potential data rates could be phenomenal, especially given their unhindered propagation. It's ultimately a matter of technological evolution, not fundamental physical constraint.
Okay, let's try and break this down then as we wrap up. What we've explored today is truly monumental, isn't it? Gravitational wave communication. It isn't actually forbidden by physics.
Right, that's the key takeaway.
Unlike trying to design, say, a perpetual motion machine, there's no inherent no-go theorem blocking it. The universe isn't saying you absolutely can't do this. It's more like it's saying you just haven't figured out how yet, and it's going to be incredibly, spectacularly difficult.
Exactly. Instead, the barriers are purely technological. The sheer difficulty of producing strong, controllable sources, which would essentially mean choreographing objects with stellar masses with unimaginable precision.
Yeah, moving stars around, basically.
Pretty much. And the extreme sensitivity required for detection, pushing the absolute limits of engineering and quantum mechanics to an extent we can barely even fathom today. It's maybe like asking someone in the 17th century to build a modern supercomputer. The fundamental principles of computation might have been nascent, but the technology was just orders and orders of magnitude away.
So why? Why does this vision matter? Why should humanity even pursue such a seemingly impossible dream, one that feels, realistically, centuries away?
Well, there are several profound implications that make this pursuit potentially worthwhile, even if the payoff is very long-term. Firstly, as we've hammered home, it offers that potentially unjammable, unstoppable channel.
The cosmic bypass.
The cosmic bypass. Gravitational waves cannot be blocked, scattered, or absorbed like electromagnetic signals. This offers unprecedented potential for security, reliability, and maybe even privacy for communication, especially across truly vast interstellar distances. Imagine a message that literally cannot be physically interfered with by any intervening cosmic phenomenon or, hypothetical hostile entity.
That's a powerful idea.
Secondly, it really is the ultimate promise of true interstellar communication, perfect, transparent connection across potentially billions of light years, linking civilizations without any cosmic interference degrading the signal. It's a way to ensure a message gets through no matter what lies between the sender and receiver.
And the journey itself.
And absolutely, beyond the direct communication application, the very pursuit of gravitational wave communication experiments, the research needed to even approach it, could significantly deepen our understanding of space-time, of quantum measurement, maybe even fundamental energy generation. It could open entirely new frontiers in fundamental physics.
The process could be as valuable as the goal.
The journey itself could be transformative, yes,
Yeah.
leading to unforeseen scientific breakthroughs. And just as technologies like radio and lasers revolutionize society in ways their early inventors couldn't possibly have imagined.
Right. Think of all the spin-offs.
Exactly. Even partial advances towards GW communication could yield incredible technological spin-offs in areas like precision sensing, quantum technology, material science, astrophysics, enhancing our lives and our understanding of the universe in totally unforeseen ways. Maybe even helping us to detect dark matter or probe the conditions of the early universe in new ways.
Like that final analogy you mentioned the paper suggests.
Right. The telegraph linked continents, fiber optics linked oceans, gravitational waves could one day link galaxies, an unbreakable bridge across the cosmos, a true interstellar internet.
That's a powerful vision, truly inspiring. And Dr. Nemoten's paper, it culminates with the prediction, right?
It does. He predicts that if future civilizations, maybe ours, maybe others, ever do harness gravitational wave communication, it would indeed be the ultimate deep space channel. Private, interference-free, cosmologically robust.
But he puts a timescale on it, a long one.
He acknowledges the vast timeline, absolutely, stating that for humanity, such technology could arise not tomorrow, not even this century, but perhaps in the far, far future, when our energy generation capabilities and our quantum precision reach levels that today we can only dimly imagine.
So this brings up a critical point for us today. What does it mean for us to explore something that is, practically speaking, centuries away?
It's about laying the groundwork, isn't it? It's about nurturing the theoretical understanding, investing in the fundamental research, even if it seems esoteric now, and constantly pushing the boundaries of our current technology in related fields like quantum sensing and astrophysics.
Building the foundations.
Exactly. It's about fostering the kind of scientific curiosity and long-term vision required so that when humanity is ready, when we perhaps achieve the necessary energy mastery and quantum control, the path towards gravitational wave communication is already illuminated by the work done today. It's about building the intellectual and scientific infrastructure for a potential interstellar future, even if that future is many generations away.
So what does this all mean for you listening right now? Perhaps the biggest takeaway from this deep dive is that exploring gravitational communication today isn't just about abstract theoretical physics. It's about preparing ourselves, as a species, for the possibility that one day it may become not just a scientific curiosity, but maybe a foundational pillar of an interstellar civilization. It really invites us to consider, what grand, seemingly impossible challenges are we choosing to explore today? What seeds are we planting right now that might transform tomorrow in ways we can't yet even imagine? What future are you helping to build, even just by engaging with ideas like this?